In this video, we'll look at a way of measuring the purity of a set of examples. If the examples are all cats, all a single class, then it's very pure. If it's all not cats, that's also very pure. But if it's somewhere in between, how do you quantify how pure is this set of examples? Let's take a look at the definition of entropy, which is a measure of the impurity of a set of data. Given a set of 6 examples like this, we have 3 cats and 3 dogs. Let's define P1 to be the fraction of examples that are cats. That is, the fraction of examples with a label 1. That's what the subscript 1 indicates. And so P1 in this example is equal to 3 out of 6. We're going to measure the impurity of a set of examples using a function called the entropy, which looks like this. The entropy function is conventionally denoted as capital H of this number P1. And the function looks like this curve over here, where the horizontal axis is P1, the fraction of cats in the sample, and the vertical axis is the value of the entropy. So in this example, where P1 is 3 out of 6 or 0.5, the value of the entropy of P1 would be equal to 1. And you notice that this curve is highest when your set of examples is 50-50, so it's most impure, has an impurity of 1, or really an entropy of 1, when your set of examples is 50-50. Whereas in contrast, if your set of examples was either all cats or all not cats, then the entropy is 0. Let's just go through a few more examples to gain further intuition about entropy and how it works. Here's a different set of examples with 5 cats and 1 dog. So P1, the fraction of positive examples, the fraction of examples labeled 1 is 5/6. And so P1 is about 0.83. And if you read off that value at about 0.83, we find that the entropy of P1 is about 0.65. And here I'm writing it only to 2 significant digits. Here's one more example. This sample of 6 images has all cats. So P1 is 6 out of 6 because all 6 are cats. And the entropy of P1 is this point over here, which is 0. And so we see that as you go from 3/6 to 6 out of 6 cats, the impurity decreases from 1 to 0, or in other words, the purity increases as you go from a 50-50 mix of cats and dogs to all cats. Let's look at a few more examples. Here's another sample with 2 cats and 4 dogs. So P1 here is 2/6, and which is 1/3. And if you read off the entropy at 0.33, it turns out to be about 0.92. And this is actually quite impure. And in particular, this set is more impure than this set because it's closer to a 50-50 mix, which is why the impurity here is 0.92 as opposed to 0.65. And finally, one last example. If we have a set of all 6 dogs, then P1 is equal to 0, and the entropy of P1 is just this number down here, which is equal to 0. So this is a 0 impurity, or this would be a completely pure set of all not cats or all dogs. Now, let's look at the actual equation for the entropy function, H of P1. Recall that P1 is the fraction of examples that are equal to cats. So if you have a sample that is 2/3 cats, then that sample must have 1/3 not cats. So let me define P0 to be equal to the fraction of examples that are not cats to be just equal to 1 minus P1. The entropy function is then defined as negative P1 log P1. And by convention, when computing entropy, we take logs to base 2. Rather than to base e. And then minus P0 log base 2 of P0. Alternatively, this is also equal to negative P1 log P1 minus 1 minus P1 log 1 minus P1. And if you were to plot this function on a computer, you find that it will be exactly this function on the left. And we take log base 2 just to make the peak of this curve equal to 1. If you were to take log of base e, or the base of natural logarithms, then that just vertically scales this function. And it'll still work, but the number has become a bit hard to interpret because the peak of the function isn't a nice round number like 1 anymore. One note on computing this function: if P1 or P0 is equal to 0, then an expression like this will look like 0 log of 0. And log of 0 is technically undefined. It's actually negative infinity. But by convention, for the purposes of computing entropy, we'll take 0 log 0 to be equal to 0, and that will correctly compute the entropy at 0 or at 1 to be equal to 0. If you're thinking that this definition of entropy looks a little bit like the definition of the logistic loss that we learned about in the last course, there is actually a mathematical rationale for why these two formulas look so similar. But you don't have to worry about it, and we won't get into it in this class. But applying this formula for entropy should work just fine when you're building a decision tree. To summarize, the entropy function is a measure of the impurity of a set of data. It starts from 0, goes up to 1, and then comes back down to 0 as a function of the fraction of positive examples in your sample. There are other functions that look like this, that go from 0 up to 1 and then back down. For example, if you look in open source packages, you may also hear about something called the Gini criteria, which is another function that looks a lot like the entropy function. And that will work well as well for building decision trees. But for the sake of simplicity in these videos, I'm going to focus on using the entropy criteria, which will usually work just fine for most applications. Now that we have this definition of entropy, in the next video, let's take a look at how you can actually use it to make decisions as to what feature to split on in a node of a decision tree.